Matt. I work at Netflix as a UI engineer, and I'm here today to talk to you about Webkit in your living room. Now, this is kind of a cheeky title, but really, on a lot of connected devices nowadays in your living room that are Netflix-enabled may be running Webkit. After tonight's presentation, I'll be able to stick around for a little while for some questions. But just to get one thing out of the way, when I tell people where I work, I wind up getting probably 3 or 4 questions, right? Pretty much is, oh, what do you think of Quick Stir? You know, oh, okay, that's great. Oh, what do you think of the split? Oh my goodness. And stock price, oh my goodness. And eventually it gets down to, so do you watch movies all day long at work? You know, like, what do you do? And I give them one canned answer. The answer is yes, I watch movies all day long at work. But in reality, we only really do that on days where we have big lunches. You know, you want to get back to work and you start watching movies. We call those days our playback testing days, right? So you get back and you hook up your headphones and you start watching Breaking Bad, and then 45 minutes go by, an hour goes by, and you go, oh shit, I need to work. So, you know, it's a little tongue-in-cheek. But when we're doing our work, we all work on this interface. So the team that I work for builds a Webkit front end that runs these interfaces. Now, the application itself is native. Part of it is used for things like the hardware, you know, touching the network, doing video playback, doing DRM, running Webkit itself. Those are all native. But the parts that are Webkit-based in our front end is all pure HTML, CSS, and JavaScript. So it's very much like traditional front-end engineering. It just has a different set of constraints. So one of the nice things, though, is when I'm at work and we do our development, we can work inside just about any Webkit browser that we want to. So for instance, these screenshots were taken in Safari. So all day at work, I get to work in Safari or Chrome. It's a real nice treat. Now, the difference in these 3 interfaces is the one in the back, this large one, we call that an LRUD interface, which stands for left to right, up, down. That's when the user has remote control, and they really just have 4 buttons and maybe an enter button in the middle. Whereas the ones on the right, those are pointer-based interfaces. So those run on things like your Wii or on TVs that have pointer devices. Now, that interface runs all over the place on tons of devices. And last count, we had something like over 450 different devices by a bunch of different manufacturers, all running our Webkit in our front end. Now, the challenge is, though, not all these devices are created equal. So when we start seeing differences in them, we can start from the bottom and know that things that touch the hardware are going to be different based on the chipset or the actual device. So, you know, the network stack, the memory bus, graphics, CPU architecture, those are all different, but they're not really interesting to a lot of us. What's interesting to us, though, in the front end, comes into things like the CPU, the GPU, and your memory. Now, sometimes memory is split, where you have main memory that runs things like JavaScript and has your objects in and all your variables, and video memory, which holds all your images. Now, sometimes we have one pool to work with where that's actually a shared resource. So this gives us a different set of challenges out there. Typical front ends don't have to deal a lot with memory. They don't have to worry about users on very, very slow devices to users on very fast devices. You just kind of pick something in the middle and shoot for it. And generally, whatever's in the middle of our desktop spectrum is still at a pretty high end when you compare it to embedded devices. As just a marker, your iPhones are about 3 times more powerful than our slowest device. So that's something to keep in mind as we go through this and talk about our constraints. So the first thing I'll talk about today is a little bit about device performance tips. Some stuff that we do to make sure that when we're running on those slow devices, that we don't go too slowly or it can give the user an experience which is suboptimal. Afterwards, we'll talk about memory, because memory is actually, oh, that's actually a spoiler alert. After that, we'll talk about some Webkit rendering basics. Just a short jaunt through Webkit, right? Because when we get to the end, we're going to talk about accelerated compositing. And the accelerated compositing will make a lot more sense if you understand some of the internals for how Webkit takes your markup and turns it into bitmaps that it shows on a device. So the first performance tip that we have is responding to user input, which in itself is not a performance tip, but the things that we do is where it comes to be interesting. So remote controls are not high-precision input devices, right? We have a mouse hooked up with USB. It tracks very fast across the screen. We click, and immediately the apps can respond in the desktop world. On these little RF remotes, when you're sitting 10, 12 feet away from your Blu-ray player and you hit a button, sometimes nothing happens. And you're like, what the hell? So you hit the button again. Nothing happens. So eventually you dig the remote out of the couch and you point it directly at it. And by this point, you're frustrated. And now that frustration directly translates to your joy using our application. if you're frustrated trying to navigate, you're not going to want to spend the time to do it. You're going to say, screw it, I'm going to go watch Hulu on my laptop and have a nice day. So for us it's really important to accept user input, provide feedback, but not necessarily update the UI all at the same time. So we handle those three vectors separately: accepting input, providing feedback, and updating the user interface. Now this is Plus. We saw this just a moment ago. This is our LRUD interface that is the core interface on the PS3, if we have any PS3 users in here. It's also the interface that runs on a lot of Blu-rays and TVs. So the interface has two big conspicuous parts, right? The part on this side, that's the gallery. The gallery can have one to many lists. There's no cap to the number of lists here that we can display. And there's actually no cap to the length of the lists that we can display either. These are just artificial numbers that we put in place to try to limit the selection to keep content discoverable. Now, that's the gallery, and that on the side, that's Bob. Bob is where we show the metadata for the selected title. Bob's an acronym. It means back of box. But it gets pretty lame and tiresome to say the Bob, the back of box all the time. So we've given it a persona. And Bob is sometimes benevolent, and sometimes Bob is really, really vengeful. And you can tell, if I go back a slide, there's a lot of individual content data fields in the Bob. For instance, synopsis, titles, ratings, runtimes, the presence of HD audio. All those things differ based on the title that you're on. So when we update the Bob, we have to perform a lot of checks and do a lot of small DOM operations. That's when Bob gets mean. So when a user is using our app, one thing that happens is the input comes in at various speeds. As developers, and front-end people specifically, we want users to hit a button, wait for us to provide feedback and update the content, and then hit a button again and do it over and over again. But users are impatient. They don't want to wait for us necessarily to update our content all the time. So we have to take steps to start providing feedback and backing off our content updates. For instance, this is me navigating around. So at first I go slowly, so Bob and the gallery both keep up. But then as I start going faster and faster, we can't update the Bob as quickly, or more truthfully, we choose not to. Now, when we go too fast, we'll actually stop updating the gallery completely too, but we still provide feedback. So that's the separation between providing feedback and providing updated content. Now you're wondering, why the hell do you do this? Those box shots are really ugly. And the truth is, they're not beautiful. But if we try to update the DOM at the same time that the animation is going on, the frame rates decrease drastically. So it's our responsibility to only update the DOM as quickly as we can still provide a smooth experience. And for instance, we can actually go pretty damn fast. If we don't limit the rate at which we accept key down repeat events, we can fly through the interface. And it looks neat, but I dare you to try to scan those titles as they fly by. You just can't do it. So one of the things which you have to keep in mind as you're handling key input is you have two kinds of key input, I guess. You have the key down and key up. You have the pair where you just click the button and release, click the button and release. You also have key down where you hold the button and then the host system is giving you those repeat events over and over and over again. Well, the rate at which you receive those key repeat events is normally pretty drastically different than the rate at which a true user can naturally hit that button as fast as they can. For instance, that video we just saw was the PS3, which does key down repeat events at 50 milliseconds apart. That's pretty damn fast. That's what, 50 hertz? Now, a user hitting the button as fast as he can in our test can only bang the button about 140 milliseconds apart. So what we do is we'll limit our response to user input to the point that we're handling key events at an interval of, say, 140 milliseconds. So if you're holding down the button, we're going to acknowledge some key events, and we're going to not acknowledge others. Now, it sounds kind of counterintuitive when you say you need to respond to user input, and here I am saying don't respond to all user input. The trick is to do it in a way that the user doesn't perceive that they're being limited, right? That's why when we measure the duration that we throttle by, it's the natural press. It's the down and it's the up. It's not the hold it down. So as we're navigating through the grid of the gallery, we're doing what we call activating. For each row in the gallery, let me back up a little bit. When we load the interface, we load the metadata for some of the rows up front. That way we can provide the user with, say, the first 5 rows. So if they navigate through slowly, they'll never see the gray boxes. But if they start navigating through quickly, then we don't have the metadata yet, and we need to start fetching it. Now, once we have that metadata, or even backing up when we try to request the metadata, we're crossing from JavaScript land to hardware land. We're touching the network interface to then make a request. Now, the speed that operation happens depends on the device. So that's the first thing that we need to try to be careful of. Once we have a response back from our API, it comes back to us as a JSON structure. And when we have that, we can't really do anything with it until we parse it. Well, parsing is a greedy operation. When you parse, JavaScript can do nothing else because parsing takes time. And if you request too much data, you're doing a lot of parsing, and everything's going to slow down, and your frame rates are going to drop to the floor, and you're going to get stutters. And the last part of the activation that takes time is actually touching the DOM. There's been people evangelizing for years that DOM is slow, and very few people, I think, actually have listened to this. Most of the time, people just keep touching the DOM whenever they want, update stuff, read properties that would cause reflows. We need to be careful about this. So we are very careful about when we update content and when we choose to have that content painted to the screen. So this paints a pretty bleak picture of row activation, but it's really not that bad. Here's a video that shows a little bit behind the scenes. This is the same application with some CSS that has, say, hidden bob. It's turned off the Chrome. It's done some scaling, turned off the overflow, et cetera, et cetera. So essentially, what the user normally sees as the gallery is that gray box in the middle. The part that's hidden from them is on the red area. That's the overflow region. So as we navigate through this, let me back up a little bit. As the user navigates through it, we have the first few columns, the first few rows of data already. But when we get to a point where we don't have the data, we have to activate all those gray rows, we stagger the activation. Now, the amount that we're staggering is exaggerated for this video. But the idea is, when you land on a row, we're going to activate that and provide you feedback as fast as possible. Now, updating the rows next to it and further out from there is less important, especially since once the user lands on one row, they may choose that they want to go someplace else. Remember, users are impatient. They don't stay in the same place very often. So if we had updated all the rows right when the user stopped, and then they chose to move somewhere immediately afterwards, it would have been very, very slow because we would have been doing a ton of network operations and a ton of DOM operations. But in this case, we do it a little bit at a time. And when you do it a little bit at a time, there's a good chance you won't have to do all the work. So this is generally how we do it. I hope you guys can see that in the back. The idea is, by default, our objects have asynchronous interfaces. So when this object is asked to activate and passed a series of IDs which need to activate, it itself is responsible for determining the best path forward to actually activating those objects. So when it comes in here, this is just straight work deferral and chunking. The first thing we do is try to defer the work. And then once the timeout has actually executed in the callback function right there, we peel off a portion of those IDs and we activate those. And then if we have any more IDs left, we set another timeout and we do it over and over and over again. Now this is what I was talking about, where the user can come in and change their idea or change their mind. And we can go ahead and drop whatever IDs haven't been activated to the floor. So internally, this object has a synchronous backer to this asynchronous method, which it's a privileged method that only this object can call because it knows about all the greedy operations that happen during that time. Now, the thing that happens, though, is sometimes we want to be able to tune that delay really far down, or we want to be able to turn it off completely for debugging. So that's why we have it as a configurable value. Because the amount that we delay in development, we want to maybe have 0. So everything runs synchronously, and we can debug anywhere along this trace. When we run this on a slower device, we might use different delays than we use on, say, a PS3, where we can activate faster. So that's a lot of words, but really it comes down to don't do everything up front. Just wait to do stuff until the last moment possible. It's all about being proactively lazy. Now, this is another way to visualize what I was talking about with when you cross a divide to the slower operations in JavaScript. And most of our code runs over here. That's all your logic. That's the stuff where you're just doing application level logic. You're determining data, you're doing arithmetic and such. But eventually, you have to use that data to, say, request more data or to update a DOM. Once you cross that divide over to the other level, you're touching different interfaces. Now, those interfaces slow down. So if you say you need to retrieve elements from the DOM, that's slow. So you want to do that as infrequently as possible. Now, this is, when I was doing some research for this, this was a big hot topic in 2009. And what's interesting is, I think some people got it in 2009, but there's still a lot of content on the web where people are still doing the same approaches, where they're willy-nilly doing all the stuff on the side, and the apps are slow for it. So if you want to try to find places to improve your app, it's kind of easy. Just target these areas first. Find out where you're doing heavy operations in that column, and fix it. Now, the second thing which is unique to what we do is memory, right? We're a long-lived application. Users can jump into our application and then sit there for hours. You know, last night I was watching Breaking Bad. I watched 3 or 4 episodes. I was in there for about 3 hours, and in the middle I was browsing around the gallery, I was looking at images, I was loading more stuff, I was doing searches. All that stuff adds up. Now, in a normal web application, you would change the location every once in a while, which would let the browser deallocate memory and clean things up so that when you start the next page, you have a fresh slate to work with. We don't have that luxury. So we need to be very cautious about how we handle the data that we have, and data being objects from JavaScript as well as images. So our application has this concept of a UI budget. Now this is something which is implied, I guess, in a lot of talks, but I think very infrequently do people actually try to determine how much memory each of their components are taking. For instance, once we take away from the total memory all the things that are also running, we're left with a much smaller budget, which means that if we start downloading tons of metadata, we need to understand that that metadata has a certain fixed size. Now, we use a lot of different approaches to try to get around that. One of the things which is also useful to understand at least, is images and video memory. Now, this is something which is not unique to what we do here. It's actually experienced a lot on the mobile world as well, where as you download an image off the internet, it comes to you compressed, right? You could have different images all come in at different sizes, and at one point, you're going to go ahead and decode those images and uncompress them and pass them to video memory. Once that decoding and uncompressing happens, that tiny image has now gotten pretty damn big. So keep in mind that the gallery has hundreds of boxes, right? And then the user goes into playback. Well, video memory already has tons of those boxes inside of it. So when we start trying to shove in there HD video stuff, it's going to chew up the video memory really fast. Now this is, in the mobile world, this is when things crash, right? You run out of memory and all of a sudden you're back at the home screen again. Same thing is true in our world too. So we have a few ways of dealing with this one. The first I already alluded to was the unbounded growth. We use a lot of caching and very intelligent caches in our code. Things like last recently used caches, and last recently used caches backed by a memory manager that understands the size of each element inside the cache. The second one, this one's kind of weird. It's minimizing the number of throwaway objects. But this leads to garbage collection, right? If you have a for loop, or you have a loop that's generating tons of temporary variables, when that loop is done, all those variables get cleaned up. So if you're doing this in a lot of places in your code in a lot of different ways, when it comes time to clean up that code, it's going to freeze the UI again, just for a moment. So your frame rate's going to go back down to 0. The user's going to look at a jerky UI and go, eh. Now, the last one's actually probably one of the most interesting things I think we do. It's pooling, right? Pooling is not a unique concept to what we're doing. It's a fundamental CS concept that says if you need, say, 10, say you're instantiating a bunch of list rows in this case, and we have a scrollable list that has 25 list rows, but we don't actually need to create 25 different list rows themselves. We can create, say, 5 of them, put them in this thing called a pool, and then when we need to display a list row, we ask the pool for a row, we format it, we use it for a little while, then we release it and put it back in the pool. That way things keep rotating like this. Now, the best way for me to understand this was actually seeing it in action. So this is just what we saw before, but pay special attention to what happens when the rows go out the top or out the bottom. See that row just disappear on top? When it disappears, it's being put back in the pool. When the rows come in from the bottom, they're going to pull that row out of a pool, format it, and then use it for the brief time that it's there. And the same thing happens on the bottom, too. Now, one of the most important optimizations that we made was being careful how we reset these elements when we put them back in the pool. Because when we put something back in the pool, we used to set it all back to the gray boxes so that when it was used again, it was ready and it was in a blank state. But what that was causing was a lot of repaints. Because as the element is visually changed, the rendering engine has to handle that in some way. So what we wound up doing was we only update them when we pull them out of the DOM. That way, we can update it one time by pulling out the old elements, the old images, image sources, putting new ones in place, and all that operation does is just trigger one paint with the rendering engine. So, yeah, this is another one of the videos that I like to watch too. Now, left and right is different. We're not actually pooling here, but we do have a fixed set of elements that we're exchanging CSS classes on. So as I navigate left and right, we're not updating the DOM. We're not changing the fundamental structure of that document tree. But we are changing the classes, which makes it look like the element's moving. It's just CSS transforms doing their magic. So this is honestly my favorite slide in the entire presentation. I just love seeing the glitter pyre get socked. Now, when we use Webkit, it's easy to get carried away with all the magic, right? It has great CSS drawing effects. And for years, we are really told that front-end performance starts with network I/O. That's true in a desktop world. But given our set of constraints, we have fast networks. Hell, you stream an HD video. What we don't have are fast devices. We have a slow CPU. We have slow GPUs. We have limited amounts of RAM. So what we wind up doing is keeping in our mind this one motto, right? And it says, don't do in software what can be handled by hardware. So that's well and good, but here's what it actually means in practice. We don't do any of these things in code. Now, it's a little odd for me to follow behind Steve and try to change some of the story. And remember, our bottleneck is CPU I/O. It's not network. Our devices are slower than your iPhones. So if I was to say paint a radial gradient or a linear gradient, that's going to cause the CPU to calculate the gradient, to render it, and to paint it. Now, if you update the contents of that element, it's going to calculate it, render it, and paint it again. If you display none of that element and show it back to the screen, it's going to calculate, render, and paint it again, right? So what we wind up doing is we use images for this, because static images are just painted. They're passed directly to hardware and is painted one time. So this does cause us to download additional images, which we use strategies around trying to make not kill our network. But our runtime performance is better for it. Because if we're going to use CSS drawing effects, they have to be recalculated and re-rendered and repainted over and over and over again. This one was actually kind of a sad one for me, because when I came from Yahoo, I was working on the front page. And we're all about fast-ass page. And the page loads in under a second. It's amazing. And a lot of that has to do with minimizing the number of requests that we make. Now, when I came into Netflix, I wanted to do the same thing. I was like, oh, this is evil, this is bad, how could you do this? And I was naive, I was from a desktop world. But on a device world, you have to acknowledge your constraints and choose the best approaches to fulfill them and still have a good UX. So keep that in mind. Don't be dogmatic, be pragmatic. Now, we do some things in software, like animation. There's no way that you can animate without software. But we only use CSS to do our animation. And that's because for CSS to do animation, it's working solely within the rendering engine. We don't use, say, request animation frame to do our animation, because that's crossing from DOM land to JavaScript land, back and forth at 60 hertz, right? And every time that your animation frame callback is executed, it blocks other operations. So what we need to do is keep our animation as close to the hardware as possible, because, like I said before, CPUs are evil and they're slow. Now, the part of this which is important to also understand is we only animate two properties. These properties are safe for hardware acceleration. We animate opacity, like fade-ins, fade-outs, and we animate transforms. Now, transforms are great because you can do scaling with transforms, you can do translations with transforms, you can rotate with transforms. They're very, very powerful. What we don't do are say, animate things like width, because as you animate width, the contents of the box are reflowed and everything is recalculated over and over again. Same thing goes for anything that changes the dimensions of the box. We're also careful not to change the contents of a box as it's animating. And these are all techniques that lead into accelerated compositing, which I'm kind of building up towards if you feel where I'm going. So before we get into accelerated compositing and really talk about hardware acceleration and how we use it, you need to understand what Webkit is and how we use Webkit. So when we use Webkit, we're not using an embedded browser. We don't have an address bar that we're hiding from you or bookmarks that we're choosing not to display or a location bar, any of that stuff. None of that's there. What we have is a programmatic API for displaying web content. Now, which is cool because being that Webkit is open sourced, when we want to try to match our content for the rendering engine, we can dive right into the source and find sources of performance optimizations. You'll see some of those tricks in a moment. And portable, we'll get into that right here. So Webkit is an engine. It's a web engine. It's not a web browser. Webkit can be put into a web browser. It can be put into a toolkit, much like a car engine can be put into a Chevy, a Dodge, or a pickup truck. It doesn't matter. It's still an engine. Now, Webkit is really composed of two primary segments, web core and JavaScript core. Now, for the rendering aspects, where we find a lot of our performance improvements, that's all inside web core. So going in there a little deeper, you think working at Netflix, I know you don't point the device at the screen. Now, web core is responsible for taking the downloaded assets, the HTML and the CSS. It parses the CSS into an object structure. The HTML is parsed into a DOM tree. And those two things are attached together. Now, the attachment process creates what's called a render tree. Now, any visible object in the DOM has a render object node in the render tree. Elements which are display none in your DOM are not part of the render tree, which is a pretty damn cool optimization, right? Why spend time painting objects which are display none or even outside of the viewport? You don't have to worry about those. Now, that's the render tree's whole job right there. Now, once you have these objects in the render tree, each object goes through a layout and a paint step. The layout is where it gets dimensions. It gets its size, it gets its position, and then from there, each object knows how to paint itself. Now, the magic in this whole process comes in the render tree and the layout, because the render objects go through a composition step, and they're created into these things called render layers. Now, multiple render objects that all share the same transform could be combined into a single layer, which is then passed along to the graphics context. Now, this is the part of the browser report that actually supports the accelerated compositing for us. Because when that layer is passed through to the graphics context, it can be turned into a bitmap and then used for accelerated compositing. It can be passed through a software for a software compositor, like it's done on Android WebKit. It's really pretty neat. Now, that was a whirlwind, 3-slide WebKit rendering basics thing, right? So we went through, you have your markup and your CSS, and in the end, you have these things called render layers. Now, the render layers play directly into accelerated compositing. Is anyone familiar with this red box? 1. All right, great. 2, great. So this is newish stuff, right? It's not new to the technology. It's been there for a long time. But we haven't really focused about this in a lot of our day-to-day work. So accelerated compositing is when these render layers are turned into bitmaps. And these bitmaps are then animated around the screen. So if you want to, say, render an object once or an element once and paint it all over the screen, then accelerated compositing is going to give you the fastest animation performance, because that element is not re-rendered and recalculated all the time. It's just moved. You just push it around the screen. So in practice, these layers look kind of like this. This is one list row from our gallery. Now we can see there's different colors, there's different boxes, there's the red boxes and the yellow boxes, but this is a good chance to understand that there's different layer types. So we have the yellow layers, which are containers, and red layers, which actually have a bitmap backing to them. So a little more explanation on Safari's visual hints. Shabak will tell you that screenshot, that magic was from Safari. The red layers are the layers that have the backing images. Those are layers that actually have the GPU textures. The yellow layers, they're called container layers. What they do is contain the composited layers, the red ones. That way, we can still get the GPU acceleration of a bunch of elements without having to, say, create one layer that is the size of that the yellow box. The cyan, I've never really understood why debugging overflow is useful. So if anyone here understands why this color happens, let me know. Basically, that's just when an element has overflow hidden or overflow whatnot, it turns cyan so we can debug it. It's kind of distracting if you ask me. Now, green ones, we don't see green ones in our UI because we keep our textures small. If you have a layer that's over 1024, it gets turned into a tiled layer by the rendering engine in the graphics context, which means that only parts of that layer render and are put in video memory at a certain time. Otherwise, if you have this giant image that's turned into a layer, you shove that in video memory, it's going to crash immediately because it just runs out of space. So to turn this on inside Safari, there is a command line flag. Default to write com Apple Safari include internal debug menu 1. That's exactly what I thought it would be, right? Now, once you turn this on, there's a debug menu that shows up in the top right corner of your menu bar inside Safari. And the two most interesting things to me at this point are the render layer tree and the show compositing borders. Remember how we talked about the render tree a moment ago has all the elements which have visual representation? Now, the render layer tree is the composited step where all those elements are aggregated into smaller layers and whatnot. So the render layer tree normally is going to map to the compositing that we saw a moment ago with the yellow composited containers and the red composited ones as well. That was a mouthful. Now, Chrome lets you bless you. Chrome lets you turn on the borders as well. If you jump into About Flags, you can go in there and turn them on. But what you miss, actually back here, is a number in the top left corner. That number is really important. That number shows the number of times that layer's content was recalculated, the number of times that it changed. For instance, before we get there, layer creation happens using CSS triggers. So in your layout, you go ahead and you can add these specific CSS properties to it, and this is going to turn that element into a layer of some sort, right? Now, at another point, if an element overlaps on an existing layer, it's going to turn into a layer as well. So what you watch out for is, as you're moving this element around the page, if it goes underneath something, that element is, the something that it goes underneath is now going to be turned into a layer right then, and then if it moves back out again, that layer is going to be destroyed. So you have to be careful where you move the elements in the page. Now, what's neat about Webkit is it's open source, right? You can jump right into the code, you can figure out what the heck's going on without having to say, ask the internet. And when I first wanted to find out this stuff, I wasn't comfortable inside Webkit source yet. So I had to go to a blog, go to Twitter, and go around searching. And 20, 30 minutes later, I finally had a list of things that seemed like they were complete. But in the end, all I had to do was go in the source. So layers are created explicitly inside right here. And we can see that things like, is it positioned? Is it overflowed? Does it have transparency? All those things lead to layer creation inside of Webkit. Now, this is the explicit layer creation. These are those CSS triggers which I just talked about. The implicit layer creation happens at composite time. That's when we determine if that element goes underneath another element. So this is one of those things, even if you don't know C++, C, what you get is the ability to peer inside and see what's happening in a way that we normally don't have the chance to do. For years, browsers were black boxes. And thankfully, browsers aren't so much black boxes anymore. So this is a short and contrived tale of two layers, right? Back when I was doing mobile stuff, there were cases where as I scrolled around the page, stuff would flicker, right? And you go, why is it flickering? Crap, and you have this deadline coming up, so you go ask the internet and you say, why is my element flickering? And it says, oh, add backface visibility, add translate Z. So you do it, and next thing you know, there's no more flicker, so you move on. But what you don't realize is the element that you added it to could have been a very, very bad element to add it to. For instance, two animated GIFs, right? One animated GIF on the left is a traditional animated GIF that just changes the contents over and over and over again. The one on the other side, that's a static GIF that's being rotated with CSS. So that number there does not ever stop growing. As long as that image is spinning on the page, that layer's contents are being recalculated and redrawn. Now, every time that new image is created, every time that number increments, a new image is being sent to the graphics context and rendered. So each frame is causing another image to be recreated over and over and over again. So this is contrived, right? But this is very true that for years we've gotten used to adding magic CSS, and if we keep doing it, we're going to have crap happening on our UIs that we want to try to avoid. So the things that are safe to change are things like opacity and transforms. Those are the things that we animate, remember from the CSS slide I spoke about? the stuff that we don't touch are the layer contents. As much as we can help it, we want to keep that layer once built and then use it as many times as possible. Now, the funny story here with the text indent is you're going, Matt, why the hell is text indent harmful for your layers? Well, we had this little 40 by 40 icon, right? It was like a left arrow. And in there we had text, and we had it hidden using text indent. And it was set to a text indent of negative 8,000 ems or something ridiculously huge. Well, what turned out is when the rendering engine made that layer was the entire size of the drawing surface all the way out to that text all the way over here. So your element visually is this big to you, but to the rendering engine, it's actually this big. So it comes down to the point where testing is incredibly important when you start dealing with layers, because you want to understand that your magic flag may have had horrific consequences that are going to crash devices in a way that you just can't understand, because who would think text indent's bad? Not me. Now, the last item in each one of the columns is they contradict each other, right? A bit. But what that goes to is if you want to hide an element that is a layer, just move it off screen. Now, if you want to destroy the element, you set it with display none. So to a user, they're both hidden. The user doesn't really perceive a difference. The device will, though. Because when you, say, try to redraw that layer again, the one that's hidden off screen just gets slid back into place. Magic. The one that was display none, that has to get recalculated, redrawn, and repainted. Now, this is both good and bad, right? When we go from playback, or from gallery, where we have tons of those images in the box shots and application Chrome, and we jump into playback where we start showing those giant images, we display none to gallery. And we do that to reclaim the video memory. Now that's one of those cases where you need to understand what's happening so you can break the rules intelligently. All right, so a lot of preaching, but here's something that's actually really tangible. This is one list row. A list row has a very simple markup. A list row is a title and is a bunch of items, and we can have one-to-many items in it. So when we look at this, we see that we have 2 red boxes, right? And we have 1 yellow box. So all those list items are one compositing layer. And the list title itself is one compositing layer. But that list row, it's a container layer. So that way, as we start to manipulate that list row up and down, it still moves as a unit, even though it has those individual painting contexts inside of it. So this is well and good for going up and down because the layer contents don't change, which is awesome. But when we go side to side, as I go left and right, the contents of the list items changes. So we need to change our layer composition to accommodate that. So when we go left and right, instead of having the list row, the list items themselves be one red layer, we break it down so that every box is a red layer. That way, as the cruise, the title on the far right, moves all the way left, we're not recreating it every time. If we had left all that as one layer, every time that thing moved, every step along the way, it would have created a new image over and over and over again. So breaking apart your layers is useful. Doing it intelligently and on purpose is what's best. Doing it on accident, that's not great. So here's the CSS that does it. It's not a lot of magic. I hope you guys can read it. Now, so we see that the list row and the list title both have translate z's of 0, right? That punches them right into a red compositing layer. Now, list items, it has a plain translate. I'll get back to that in a sec. Now we see for every sequence of those boxes, CT is the class that we put on each box. We give that a translate X as well. Now, once we go left and right, we actually stick a translate Z onto all those sequence images, on all the sequence classes. And what we've noticed is that if you give something a translate Z, Webkit is going to take and make that a red border right away for you. It's going to punch it into a red border, and you're responsible, you as a developer have specifically said, this is a compositing layer, make it red. Yet, when we use just a plain transform, or excuse me, a plain translate X, translate Y, or just translate, what we get is we give Webkit the ability to composite those layers the best way it sees fit. So that's why when we're not animating left and right, the list items and all the boxes on the side of it are just red layers, or they get bubbled up into one layer, right? Let me go back again. So none of those list items, those boxes have translate Z. They're not being punched into layers. Once we go up here, we start punching them into layers. Great. All right, so that is accelerated compositing. It's a pretty cool topic. It's something which definitely relates to mobile and to devices and to desktop. You can use this on the desktop, but you won't really feel the difference on the desktop because most of the devices that run desktop web apps are fast. And you open something up on your MacBook Pro, it just flies. But when you start going to slower devices and things that are slower than your iPhone, that's when you need to start pushing stuff out of the CPU and into hardware. Now, the last bullet there, trial and error, I'll just harp on that one more time. This is the trial and error comes down to things like that text indent bug, right? Where you add it and you think that that layer is great, but quietly the rendering engine says, no, it's actually this big. So that's a good example of error. And we've had a lot of those as we tried to come up with the best composition for our gallery and for different parts of our app. It's a lot of try it, test it, try it, test it, try it, test it, just like most performance updates. Except now we're not really dealing with JavaScript runtime performance or network I/O. We're dealing with how fast can we move these graphics layers around the screen. So that is my talk today. I really thank you all for coming. And thank you. Good question. Estelle's question was, if we take a layer that's already built and we push it off screen, it's still in memory, right? So to our app, we haven't reclaimed anything. That's absolutely true. So when we do that, we're careful about it. And we do it in places, typically it's a fast interaction. Like say we toggle a panel that shows up and fades away like that. We'll do that with off-screen. That way next time it shows up, it's closer to instantaneous. Once we do things like change the overall state of the application, something like entering playback, that's when we really flush as much as we can. So the question is, how do we know when we have too many layers in screen, in video memory? And typically for us, that's when things start slowing down a lot. Because when you run out of video memory, all those animation operations go to hardware, go to software. So it's more of a reactive operation. We don't have a way to measure our individual video memory usage at a certain point in time. All right, I'll be up here, and you guys can come ask more questions if you want. Thanks a lot.